test is called the Leibniz. That's how I'm going to go with the pronunciation there. Leibniz, I guess, test for alternate series. For alternating, I'll just put, I'll abbreviate it like this for future reference. So this is for alternating series. So this says that we are assuming, so assume that sequence A sub n is a positive sequence that is decreasing. So positive, decreasing, and this is an important and, converges to 0. Converges to 0. So in other words, limit as n goes to infinity of this sequence equals 0, right? That's what convergence to 0 is. The limit goes to 0. Then, so after we assume this, then we could say that the infinite sum, as n goes from 1 to infinity, of -1 to the n minus 1, an, so we recognize this as the form of an alternating series, right? Then this converges. Converges. Okay, so that's the main statement of it. That's basically just what it's saying. And also, there are a couple other side notes here that S, the sum here, the infinite sum, is going to be between 0 and A1. And there's another thing, S sub 2n is less than S itself. So this again is the infinite sum, and which is less than S sub 2n plus 1. And I'll explain this. And this is all for n is greater than or equal to 1. So basically on our number line again, what we have here is, let's say we're starting at 0, right? And then we have A1 going all the way over here. So A1's here, so S1 is here. Okay, and then we have A2 traveling back some, backtracking, I guess you can consider it. And then S2's here, and then let's say S3's over here. Okay, and I'll draw out 4 of them. But there's obviously an infinite number. So this is a plus A3, and I'll do one more for A4. Okay, so this is a minus A4. So this is our partial sum, the fourth partial sums, and then we have like 5, 6, 7, 8, 9. Let's say our infinite sum is here eventually. Okay, so this, what these statements are saying, we can see that they're true on the number line, right? So our S, which I've highlighted here, that's in between 0 and A1, right? Because A1, that's basically just S1 equals A1, because that's only the sum of the first term alone. So it is in between, we can see that. And let's check this statement as well. So for n is greater than or equal to 1, then we could prove that, here, I'll write it over here. Let's say we plug in 1 for n, so then this is S sub 2 is less than S sub 3, right? 2 times 1 plus 1 is 3. So this is basically saying the infinite sum, so what I've circled, is between the second and third partial sums. So here's the second and the third, and this is in fact in between. And if you plug in, let's say, a 2 for n, then that would mean it's in between S sub 4 and S sub 5, which it would be, S sub 4 and S sub 5. And it's basically saying that its neighboring partial sums, it's always in between them. So anyways, that's it for the Leibniz test for alternating series. Okay, now on to another theorem. So this is a theorem now, not a test. So theorem, this one says your partial sums equals from n equals 1 to infinity of the alternating series here, an. So then this is saying basically the same thing as the Leibniz test, but just in formal terms. So this is just that when we have something like this in alternating series, right, then we say that the sequence an, if it is positive and decreasing, and that it converges to 0, then it's an, well, this, it's kind of just the statement of it, but then from this theorem here, we get that this, and I'm going to write it out and then I'll explain it. So S, the infinite sums minus any given partial sums, is less than A sub n plus 1. And that's a capital N. Hold on. Let me go back here. This is a capital N, just so it matches with this one over here. So basically, this says that the infinite sums minus partial sums. So this is technically, this should look a little bit familiar because we've done this before. So the error that we incur due to taking a certain partial sums is less than, and this represents the first omitted term. And we ran into this when we were doing some of the midpoint approximations, the trapezoidal approximations, and the Simpsons approximations, and also Taylor polynomials, if you'll remember. Yeah, so a depiction of this would look like, so we can visualize it a little bit better. So let's say we have our 0 and then S1. Okay, and then you get the idea, remember? So I've done this a couple times already. And then we have S4, S5. Okay, and then I'll draw in these. So let's say we have A1 going across here, so plus A1. And then we have a minus A2 going from here to here. And then we have a plus A3. And I'll just do one more after this. So this is the plus A3. And then the minus A4. Okay. Minus A4. Okay, so what this is saying, let's say we do, we're calculating the third partial sums. Okay, so this is the one that we're looking at here. But the error that we would get, so this represents error. So the error has to be less than A sub n plus 1. So n would be 3, right? Because we're taking S sub n. So n is 3 plus 1 would be 4 on this side. So this is saying that the error, the distance between, let's say our infinite sums is here. So this is our infinite one. So the distance between here and here, so this right here, what I'm kind of like bolding out, this distance has to be less than the length of A4. So the length of A4 is this line here. Disregard the negative for now. The negative just means the direction it's going in. And we can see that that's true, right? The distance between S and S3 is less than this whole length of A4. Okay?